Hello everyone, so we're just now on page 12 of the Forces Booklet B, and we are given examples of how to prove that through the principles of moments, that a force on either side of a pivot is balanced. And the thing to remember here is that the longer the distance from the pivot, okay, so the longer the distance from the pivot you are, the greater the force that you will achieve. So in other words, to put that into some sort of question here, we have our pivot. Okay, this is the pivot here. And we're looking at two masses, okay? So we have a mass here of mass A, and mass A is 350 newtons, and it is 1.4 meters away from the pivot. Then if you look at mass B, we can see that it is 2.8 meters from the pivot. And we are asking this question, what would the mass or the force of this mass be? What would it have to be in order for the whole thing to be balanced? Okay. So the beam is balanced. And when you see that it's balanced, that means then you have to write out two simultaneous equations, if you like, two going along each side, okay? Because if you can think about it here, we have a movement. This force here is forcing the beam down and round, and that would be a clockwise motion. And to counterbalance it then on the other side, we have an anti-clockwise motion. Just remember that every force has an equal and opposite reaction. Every action has an equal and opposite reaction. Okay, so we need to balance out the anti-clockwise. So we'll just say anti-clockwise ACW, and clockwise is just CW. We need to work out then what formula we're going to use. The formula for moments is moment equals force times distance. Okay, so we need to write out force times distance equals this force times distance, because we want to have them balanced. We know that force A is 350, and we're going to multiply that by our distance, which is 1.4 meters. On this side, we don't know what our force is, but we do know that it is 2.8 meters away from the pivot. Now, we want to get force, this F force, on its own. So how do we achieve that? Well, we bring the 2.8 distance value, that's multiplying over here, and we want to bring it over, and it will be dividing then. Okay, so if we multiply 350 times 1.4, we get 490, and that's divided by 2.8 equals F. Okay, that's what we're trying to find. We're trying to find the force F here. So when we put that into our calculator, we get 175 equals B force. Now, this is just a number. It hasn't given us any details of what it is. We're trying to find the moment, and moments are measured in newtons and D for distance, which would be meters. So we had newtons here and we had meters here. So the answer is 175 Newton meters. Okay, so we can see that you need a force of 350 if you are a short distance away from the pivot here. But if we extend our distance, if we double our distance from 1.4 to 2.8, then we halve the force that we need. Half of 350 is 175. So we'll just have another look at an example here, and remember that the forces are balanced. How do we know? Well, the beam is in a straight line. In a question, you'll be told if it's not balanced or not, but it just presume that it is balanced because we have this straight line. So have a look at what we have. Here is our pivot, and our distance for this movement here is 0.5 meters, and we have a force of 5 newtons. Okay, so if we just bear that in mind, that will be our D for distance, and this is our F for force. On this side, that would be the clockwise direction, going this way. On the other side, in the opposite direction, we have the distance is 0.25, and we're asked to find the force. So what force will it be if we have halved our distance? Okay, so if you have this distance and it's 5 newtons, if we halve the force, then if we halve the distance, we're going to double the force. Okay, so you would sort of anticipate it that it's going to be 10 newtons. So we need to prove that. So we'll just write down what we have here. That's our distance, and this is our force. So again, we need to state the formula that we're using, and we know that moments equals force times distance. So we have our anti-clockwise movement here and our clockwise movement on the other side. We're using the formula force times distance. We know that it's balanced, so we're going to equals that. Okay. Now on this side of the anti-clockwise, we have our force we don't know, and our distance is 0.25, which is equal to a force of 5 multiplied by 0.5. So we'll just calculate that out. We have 0.25 F, there's no need to put the times in, is equal to, when we multiply that out, we get 2.5. We want to get this F on its own. Okay, so we bring the 0.25 over. It is multiplying here, so we divide it on the opposite side. It changes sign. So now we have F is equal to 2.5 divided by 0.25. And if we slot that into the calculator, we get F equals 10. Okay, now we want to know what the force is. So the force is in newtons, so it was a force of 10. And just to go back, if we know anything about the principle of moments, we know that if you half or if you double the distance, you half the force. So we have half the force. 0.25 is half of 0.5. So then we must double the force. And we had a force here, 510 or 5 newtons. So here it would be 10 newtons. And that is what we got in our answer here. So up until now, we have been looking at the moment or the turning force on a pivot, and we just see it in actual 3D terms of, say, on a seesaw or a spanner or the brakes on the handlebar of a bicycle. Now we're going to take a closer look, and this involves the centre of mass. And the centre of mass is the point about which the mass of the object is acted on. Okay, so you don't actually see this happening, but every object or every mass has a centre of mass of where it will operate from. Okay, you would notice it, say, in the difference between a Formula 1 car and a double-decker bus. the centre of gravity or the centre of mass of that Formula One car is quite low, so it won't topple over as easily as what the double-decker bus would. Okay, so it's all to do again with the distance from the pivot, or the, in this case it's the, in a larger object, it's the distance between or from the pivot or the centre of mass in this case. So we want to find the centre of mass in each of the following, and basically this is usually a question that is worth 1 or 2 marks depending on what type of a diagram they're going to give you. And basically, to find the centre of mass, you draw 2 straight lines that are crossing each other at right angles. Okay, so for instance, if we draw one here and another one there, we're basically just putting an X. The centre of mass is right in the centre. Okay, and sometimes this is called the centre of gravity. And it's very important in making toys for children, because the lower the toy has, the lower the centre of gravity, it won't topple up over on that child. So sometimes it's called centre of gravity, or COG for short. If we have a square item, we just take it across the points here, and where it dissects, here is the centre of gravity. Again, this could be like a cylinder or a wheel, and you just draw an X and it'll be in the centre here. So this is where we see the centre of gravity. Now that is page 12 complete. I will stop the video here so that we can move on to page 13 and investigate the centre of mass further.